Okay, today we are going to learn about buoyancy. And what is buoyancy? What does it mean to be buoyant? To float. You can float in any fluid. And buoyancy is basically an upward force that exists because you are in a fluid. Now, to understand that, you have to understand what is a fluid. A fluid is anything that flows. So if it can flow, it's a fluid, and so basically we have two types of fluids. We have liquids, and we have gases. The liquids and gases are both fluids. Solids don't flow very well, so they're not a fluid. So liquids and gases can exert a buoyant force. A buoyant force always goes upward. It doesn't go down, it goes upward. Why does it go upward? It goes upward because if we are underwater, if I'm underwater, is there more pressure on the top of this or on the bottom of this? There's more pressure on the bottom of this because on the top I have this much water over it, but on the bottom I have this much water over it. So I have more pressure on the bottom than I do at the top. So on this object, the bottom always has a bigger pressure and the top always has a smaller pressure, which means we have a net force going from big pressure to small pressure upward. It's always going to be that way. If I sink it lower down here, did it change any? No, this is still a certain amount of pressure and this is more pressure because there's more fluid. So it's still the same thing. So I have the same buoyant force in both spots. There was a guy who figured out buoyancy. Anybody know who the first guy to figure out buoyancy was? Mr. Buoyant. Mr. Buoyant himself. There's an ancient Greek guy named Archimedes, and Archimedes was the first guy who did some serious study on buoyancy, and he noticed some things. And so we have, excuse me, Archimedes' principle basically says that the buoyant force is equal, I can write, to the weight of the displaced fluid. So the buoyant force is equal to the weight of the displaced fluid. So if I stick you underwater, you displace a certain amount of fluid, and if I weigh how much water that is, that's how hard you're being pushed up with. What that turns out in formula form, FB stands for buoyant force. That was pretty. we end up with FB equals V rho G. The reason that second letter looks weird is it's Greek. Because Archimedes was Greek. No. The reason we do it this way, it's a little easier. If it's the weight of the displaced fluid, what is weight? Mass times gravity. Really tough, right? But here we're dealing with this funny symbol. This funny symbol is equal to the density. And if you learned about density, you learned that density equals mass over volume. So if I bring the volume over here, that's equal to mass. So I can take mass out and replace it with these. Hey, that turns out to be the same formula, right? Now, that works fine if you were looking at forces. There is a shortcut that you can kind of do. If you don't want to deal with the weight of the displaced fluid, you could deal with the mass of the displaced fluid. And if I get rid of, if the buoyant force is equal to the weight there, again, the mg, I can cross off g on both sides. And I can say the mass of the fluid so, yeah, and that'll tell me how much less mass it has. So that can be a shortcut that comes up later, but for now, we'll ignore the shortcut. And we'll go back to where it used to be. So FB equals V rho G, and rho is density. So the density isn't the density of the object that's underwater, the density is the density of the fluid, and the volume is the volume of that fluid that's being displaced. So if you're a little boat on the water, the boat sinks down to what point? This much of the boat is underwater. And so it sinks down until the weight of the boat and the buoyant force balance out. They're in equilibrium.
Yes.
So if I put like a beach ball on the water, how hard does the beach ball go into the water? Yeah, we pretty much have the beach ball sitting there, and this is an exaggeration because not even that much would go underwater.
Yeah.
Why is that?
It's not that much gas.
The beach ball is very, very light in weight, and so if you have very little weight pushing down, you don't need to displace very much fluid before it sinks. But if you jump on top of the beach ball, if you're holding onto it, then suddenly the ball is going to sink down to here, because now it's also holding you on there. So you're grabbing onto it with your big old head. And you're underwater. Now, when you go in the water, do you go all the way under? Well, you do if you jump, but you'll pop back up.
Yeah.
Unless you're a sinker. Is anybody in here a sinker?
Maybe. Yeah. I'm not that sure.
Well, if you actually, for most people, it comes out to how much air is in your lungs. When you expand your lungs, your chest gets a little bit bigger, and so you displace a little bit more fluid, and so you become, since we're mostly water, we're pretty good with that. So if our lungs are filled with air and our chest is a little bigger, we're usually, well, usually for me, the water's right about here, so my nose is above, not necessarily my mouth. And so I hang out up here and I need to breathe through my nose and I'm fine. But if I exhale, then my chest becomes a little smaller, I displace a little less, so I have to sink a little more to equalize that out. I have several children who are sinkers. Africans tend to be sinkers. Their bone density is higher. And so they have a tendency to be sinkers. So it was funny when we were teaching them to swim because our biological children, no problem, we just stuck them in the water and taught them how to float because they floated, and we were teaching our Africans how to float and they kept sinking. It's like, you're doing this wrong, and they weren't doing it wrong, and they were just sinkers. So, yeah. Anyway, so you're going to sink to a point where you're in equilibrium there. How many of you guys ever picked up somebody in the pool before? That was like fun when you were a little kid, right? You're little, and all of a sudden it's like, look, I could pick up my dad. And you were so excited because you were so strong. And you weren't really strong because underwater your dad is pretty much weightless. And he's there and you're holding on to him, but you don't have to do much to hold on to him. You can like push with one finger and get him to float because he's floating pretty much without you. But if you start to actually pick him up out of the water, then he gets heavy, right?
Yes.
Or if you ever went over to a diving board, like if you had water and there was a diving board here, and I used to do that where I would reach up and grab the diving board, and you do chin-ups on the diving board. And the beginning is really easy because most of you is underwater, but the farther you get out of the water, then the harder it gets to blow, which is great because you get stronger when you're down here anyway. So it works out really nice. You do great chin-ups and that way. So, yeah. Now, what if we're in air? If we're in air, do we have a buoyant force? Yes, we do. Because we still have Fd equals V rho g. So we have to say, well, what is your volume? How many liters am I?
20.
Okay, so say I'm about 30 liters of volume, and then of course G is going to be 9.81. We just have to figure out, well, what is the density of air? How would we find that out?
Molecules per.
That would be where you look on the chart on your piece of paper, where you have a chart of a bunch of densities of different substances. Why would I include that in this unit, I wonder? So you look there for air, and you find that the air density is 0.00 what? 118.
Yes.
So you multiply that out. .00118 times 30 times 9.81, and that's a whole 0.347 newtons of force. I feel so much lighter now. So yeah, if we pulled all the air out of the room, you would actually be that much heavier. Is that very significant? No. That's why it doesn't work too well. We don't float around. Now, why does like a helium balloon float around? Helium is less dense than regular air is, and so it has, if its density is a little bit smaller than that, then its weight is smaller than that, so the buoyant force going up is a little bit bigger than the weight, so it's going to go up until it hits a density of air that's equal to itself, which is higher. So that's going to work. What about hot air balloons? How do they work? When any gas heats up, the molecules expand. As it expands, it's less dense, same mass in a bigger area, so it becomes less dense. If it's less dense, then it's going to go up like that again. So it's that buoyant force becomes bigger. So for a hot air balloon, if you want to bring you up, you have to have this balloon that's like this big, and you're here. So, and you get it right in a little bucket down there. But the balloon has to be enormous compared to you because the difference between hot air and cold air has to displace your mass as well as its mass, so you gotta have quite a bit of it. So they regulate the height by regulating the temperature, so they have a little flamethrower in there to heat up the air when they need to go up and let it cool when it's going down. Super duper easy. Now, what if I have water and underneath the water I have a rock? Is it going to float?
No.
No, it's going to sink. But is it going to weigh as much underwater as it did above water? It weighs less. It's actually easier to move heavy stuff underwater than it is to move heavy stuff over the land. Because when you're underwater, it weighs a little less. Underwater what?
Gym.
Underwater gym, yeah. You can have water aerobics, but that's usually just using the resistance of the water. Which is nice too, because you get resistance in a different way. But yeah, say we have something that's 1 liter and it weighs 3 kilograms in the air. How much would it weigh underwater? Well, if again we have dFd equals v rho g and our volume is 1 liter, the density of water is 1. That's a really tough number to work with, right? And so then G is 9.81. So if you have 1 liter underneath nice clean water, you're going to have a buoyant force of 9.81. Well, above land, it's going to have 3 times 9.81. So its total weight above the water is
29.43.
Yeah, so that's 29.43 in the air, but then when we're underwater, I get to subtract that out because that's pushing up. So underwater, I only weigh 19.62. So I basically went from 3 G's to 2 G's when I was underwater.
You should go the other way, from 3G to 4G.
Sure. Okay.
1G.
Easy, right? Okay, so I'm going to set you free to do a few problems and see if you can get your hands on the math of it. And tomorrow we'll have a competition on some things, and we'll wait and see if we can get some more 3-liter bottles and